Okay, now so let us come to a quick point, that is level of ionization. Which we have already talked about, but let us see it again in order to declare it to be completed. Like level of ionization is, what do I mean to say with this? Let donor impurity concentration, and obviously for n-type is ND, and that is obviously per centimeter cube, and let acceptor impurity concentration, that is obviously p-type, and that is, let's say, Na. So these are the figures for number of atoms we have introduced externally. So we know what happens. Let's take this example. So either this or this case, both the cases cannot happen simultaneously, but in order to have the similar results, I am taking them parallelly. Okay, so assume that I'm assuming the case of n-type, and I have said there are some atomic arrangements. I'm not going into the detail. Very roughly we can understand this. So suppose this is the intrinsic scenario. There are well tightly packed silicon atoms sharing covalent bonds with each other, and therefore they are very well bounded with each other. And then if an impurity comes from externally, like this, it comes, some phosphorus atom comes, and then it replaces this. Then this center is basically declared, or this was the valid lattice point, or valid lattice center. Means when it comes here, it quickly donates one electron, because it is then governed by such electrical or electronic wave function, so that it quickly, for that to understand we need to go much into detail of crystal theory, but that is not required here. So we can understand, if it comes to a valid lattice point replacing one original silicon atom from there, then this, it quickly donates, or this thing is understood by this, that as soon as it comes inside, momentarily it introduces, like this was EC, this was EV. So momentarily it introduces one donor energy level ED, which is just below, almost around 0.05 electron volt or 0.045 electron volts. We have already seen this is the ionization energy, this difference. So as soon as it comes here, because the thermal environment or thermal energy is far more sufficient to have this transition from, so one electron was here, so very quickly it comes here automatically, like the thermal energy itself is sufficient enough to knock it out. So therefore the one extra electron, because it has got 5 electrons in the outermost shell, so one extra electron will quickly come out and will be ready to move anywhere. So that is understood by this scenario. But if same thing happens with this, so earlier the scenario was this, but the same P phosphorus atom comes and goes and sits somewhere here, then this was not a valid lattice point. Is not a very perfect technical term, but by the valid lattice point I just want to elaborate that this is an allowed position or scenario, though its probability is far low. But when this happens, then it doesn't donate any electron. So the electron is not released. So because in this void, this gap is called void space. In the void space, it is governed by, or it is surrounded by such energy functions which are not favorable enough to release that electron quickly. So therefore the electron will be attached at this position, or you must say the ED is lying somewhere else at E-D, and it is not allowed. So this transition is not allowed here, or in fact you can say ED is not lying at the same level ED here. So won't be any ED provided by, like in other words you can say this, there will not be any reliable ED or donor energy level will be introduced into this. So if there is not this ED which is just below the EC, so you cannot have any transition and the electron is not ready to. So such a probability is very, very low at room temperature or near room temperature and at higher temperature. So what happens, let me quote it like this. Electron is, let's say, Nd. So what is the result? And this I am writing for N-type. So for N-type, if we are trying to make it N-type, then we inserted Nd. Out of Nd, only Nd plus. I'm just elaborating because whenever one atom releases one of its electron or donates one of its electron, the remaining atom which is deficient by one electron becomes a positive ion. So it is a general tendency to, a general convention to indicate it like this. Okay, so then definitely Nd plus is, Nd plus is Nd minus small nd. So this is the favorable amount, or this is the purposeful number of atoms which are required. So these are the purposeful concentration. So whatever numerical we proceed further, will be proceeding with this amount. So then these two figures will be provided to us. Either this thing will be directly provided to us that not 100% have donated. So let's find the percentage of ionization. So how many percent of atoms have been ionized? Ionized means those atoms who have donated their one electron, means Nd plus. So obviously it is Nd plus upon Nd into 100. So if percentage of ionization is given to you and if Nd is also given to you, then very quickly we can find Nd plus. Oh, I'm sorry again. Or this thing is same as Nd plus, you can anytime write Nd minus or Nd upon Nd into 100. So let's say you inserted 100 atoms. Out of 100 atoms, only 80 atoms donated their one electron, and remaining 20 atoms they could not find the valid lattice point and they are trapped into some voids. So therefore the percentage of ionization, relevant ionization, will only be 0.8, a fraction, or 80%. So like that we can proceed. The same thing could be happen with the p-type. So let me quantify this. For p-type, number of atoms ionized. So let me take another term. Donated one electron means ionized. Oh sorry, here donated one hole. So ionized or donating one hole. So when they donate one hole, any atom donates one hole, means it is deficient by one positive charge, so it is indicated as Na minus. So out of Na minus have donated, they are the purposeful amount or the desirable amount, and number of atoms not or unionized, let me call unionized. Unionized is same as not donating one hole here. So that is Na. Then again we can write Na minus is Na minus Na. And anytime you can find the percentage of ionization is Na minus upon Na into 100%. So maybe in some problems it is not directly given to us. If it is given that there is only 95% ionization, then out of total doping we can calculate Nd plus and Na minus. So wherever we have used Nd and Na, we'll be using Nd plus and Na plus because they are the relevant figure, they are the purposeful figures or the main figures which we are looking for. Okay, now there could be two extremes. As we analytically understand this, that we can say there could be one case we call freeze out condition. Freeze out condition is when everything is freezed out with respect to temperature, we call it, means at T is equals to 0 degree Kelvin or very close to it. So if temperature is near about absolute zero, almost, means it cannot be at absolute zero, it is only a hypothetical figure, but suppose if it happens, just for reference, or very very close to it, then we have seen that the thermal energy kT is almost zero, almost or exactly 0 electron volts. So whatever atoms have been donated to, or atoms have been inserted to as an impurity inserted into the silicon, are not able enough to provide their one electron or one hole, because the thermal energy is not sufficient enough to knock them out. Though it appears very contradictory or hypothetical point, because in any process when you are trying to insert something inside, it cannot, the process itself cannot happen at freeze out condition, but it is only hypothetical just to make a reference point that if suppose it happens that temperature is almost zero or very very close to zero, and we are still capable enough of taking this process of diffusion or ion implantation, and once that happens and energy is not sufficient enough, so there won't be any transition from donor level to conduction band or acceptor level to valence band. So electron and holes will not get free from that impurity atom. So there won't be any contribution from the added impurity. So therefore, in this case, from this terminology we can say that Nd is equals to Nd or Nd plus is 0. So this is quite unfortunate. Or if it is p-type, then Na, number of atoms who haven't got ionized, is same as the total concentration. So not even a single atom has got ionized, so they are not donating, not contributing anything. So therefore Na plus is got 0. From these relations you can conclude this. So this is a great extent of disappointment, because this is completely a disappointing case, and be happy because it is never going to happen, because this only happens at very very extreme cases or extreme conditions which are only hypothetical. So there is almost very very poor probability of this thing to happen at room temperature or near about room temperature. So the second case which we can say, so just forget about this case, very very rare, just to discuss this. Second case is complete ionization. This is the case which we are by default looking for. Every time in any numerical or any problem statement, we are by default assuming this case. And this case says that at room temperature or near about it, means not strictly near about it, or any temperature greater than room temperature. So higher temperature is beneficial thing, because at high thermal energy it guarantees, or it makes a better probability that definitely the electron which is into the outermost shell of the impurity is definitely knocked out, or the hole is definitely knocked out. So the contribution definitely happens, is confirmed, or is confirmed by a higher probability when the temperature is higher. So then Nd, so the number of atoms which are not contributing into the ionization, they are very very poor, it goes to 0 almost. So therefore Nd plus will be approximately Nd, and that is what we were looking for. Similarly for p-type, it is Na goes to approximately 0, means there is nobody or there is very poor probability that some atom is not contributing any hole or electron. So therefore this is approximately 0 and Na minus is approximately Na. So if it is not said, if it is not provided, we always by default take this case, and it is a relevant scenario as well, because we know that it is almost illogical if we do a lot of effort in placing a highly complicated ion implantation or diffusion setup, and ultimately we are not getting the objective which we are looking for. So the thermal energy, we ensure that the process itself is highly energetic, or it involves a lot of energy, basically an implantation, that it in itself ensures that as soon as a impurity atom enters inside the silicon structure, it definitely finds a lattice point, or after lots of study only we have identified that with silicon the probability of complete ionization is very high for phosphorus specifically, and similarly for boron specifically. So that after that only we conclude that silicon with phosphorus for n-type or with boron for p-type is a good combination. So we will always be considering this case if nothing is mentioned. So now onwards I'll take Nd and Na symbols only, assuming that there is a case of complete ionization. But now we know that if it is not the case of complete ionization, then how to proceed, now that we know. So now let us quickly cover the case of composite doping, or I must say the rigorous calculations of the doping concentration or the final concentration when doping concentrations are not much higher than the starting intrinsic concentrations. If they are much higher than that, then we very well know that in the case of n-type semiconductor, the majority carrier concentration, that is electrons concentration, is approximately equals to Nd, and therefore we can calculate the minority carrier concentration, that is of holes, using mass action law. Similarly, if it is a case of p-type, then we know if the doping concentration is much higher than at least 2 order or more than that to the intrinsic concentration, then we know that the final hole concentration into the p-type will be the approximately same as the impurity concentration Na, and then we can very easily calculate the minority carrier, that is electron concentration, using the mass action law. But the point comes when either we have mixed both type of doping, we can do this, or sometimes actually it's a practical scenario which is automatically happening. In the integrated circuit process, there is already either a p-type or an n-type substrate available, or some local region is available onto which we are doping or implanting some external impurities. Like already we have a p-type substrate, and onto that within a well-defined region we are targeting to dope the holes, or we are trying to make it p-type. Similarly n-type. Similarly, we may already have an n-type big region, and onto that we can try to develop a p-type region, local p-type region. So it is not every time like p and n are separate. We already have some type of region which is already governing majority carrier like electrons, minority carrier as holes. We are forcing from outside, we are inserting lots of impurity which inverts it, which makes it locally as a p-type, means majority carrier becomes holes and minority carrier becomes electron. So therefore, in order to understand this complicated process, let us generalize our understanding. So let us assume this case when we are doing both types of doping, when some Na trivalent impurity concentration is also added into intrinsic semiconductor, and Nd, caps lock Nd, is also inserted into the intrinsic semiconductor, and then see what happens, what is the final concentration of electron and holes, and what happens finally. So let us quickly look at this. So let us assume that we are doping with Na and Nd. These are the impurity concentration, Na number of atoms of trivalent impurity per unit volume, that is per centimeter cube, and these number of atoms of pentavalent impurity per unit volume, that is per centimeter cube. So those many atoms, and we are considering by default, I have already ensured that we are always considering a case of complete ionization. So until and unless told to us, we will always by default assume complete ionization. So as soon as we dope it with any number of atoms, any number of holes are provided as free holes. Nd number of free electrons will be provided to the silicon. So with that, what will be the final scenario? So let me make a chart of it like this. So earlier we had intrinsic semiconductor, and here we had N is equals to Ni, we had P is equals to Ni. Okay, and just to elaborate it, intrinsic and to differentiate between intrinsic and extrinsic concentration I'll be highlighting as N0 and P0. So earlier it was this, then we added it with Nd and Na, both we are doing. This time we are doing it simultaneously, let's say, and they may not be equal, there may be a difference. So they may have some different value, they are independent to each other. So as soon as we do, then what will happen? See, what should happen is that some fraction of Nd will get cancelled with the holes, or as soon as the holes find that, let's only assume that Nd has come into the picture. We have already seen this case, so let us quickly wind it up. That as soon as holes they find that lots of electrons are provided, so all the holes will try to terminate their existence, or they will try to recombine with them. So therefore the hole concentration will go to a very, very low value. But please remember, the holes concentration is already very low, 10 to the power 10, and Nd could be very, very high, 10 to the power 14 or 10 to the power 15. So in order to compensate with 10 to the power 10 holes, only 10 to the power 10 electrons are being recombined, or they are compensated. So what remains after that is still 10 to the power 14 or 15, because we are taking only 10 to the power 10 electrons from here to have recombinations with them. So still almost all electrons are still left, which are externally inserted. Okay, then they all are going and they are increasing, they are adding up with Ni or with N. So N plus Nd makes it approximately Nd, because Nd still is 4 or 5 order more than this N. So therefore the same story will happen with Na. So Na concentration, as soon as lots of holes are inserted into the intrinsic, then all the electrons will try to recombine with them. So some part of this, because this is like an ocean from where you have taken some tunnel, or you have drawn some tunnel of water, so it doesn't make any effect onto the water content of that ocean. So therefore some part of that will go and recombine with electrons, and it will be, the figure in itself will remain intact. So then Na plus P will make you some final concentration. So let's say being done, all these things have been done, and after that the final concentration of electron, that means free electrons only, is, let's say, N0, and final concentration of holes is, let's say, P0. Okay, then there comes a very, very important law, that is charge neutrality. For this, a very small comment. First of all, let us assume we are only making an N-type semiconductor. So into the intrinsic semiconductor, what is the total polarity or total polarization or polarity nature of an intrinsic semiconductor? Is it ionized, or it is unionized, or it is having some resultant positive charge or negative charge? So actually an intrinsic semiconductor, because it is having either all neutral atoms, or it is having some electrons and holes, but because holes and electrons are always equal in amount in intrinsic, as well as whichever atom has donated electron, the same number of atoms have donated holes as well. So in all the respect, the total charge, net charge within the intrinsic semiconductor will remain same. So an intrinsic semiconductor box or material as a piece in totality is neutral always. Similarly, if we start with this intrinsic semiconductor, and if we dope some extrinsic, the impurity, like we only do Nd, then once it becomes N-type, let's say, then what is the total charge as a totality for this extrinsic semiconductor when it becomes N-type? Then only it remains neutral, because whatever atom has come inside was neutral actually. in the impurity atom. Once it enters inside the silicon, it donates one electron. So we assume that one electron has been donated, so there should be excess of negative charge, but one electron is equally balanced by the ion left behind. So it has got detached from an atom which has now become an ion, a positive ion. So always a positive ion and one electron makes a neutral entity, and therefore all the external impurity insertion was neutral. So at the end, the n-type and p-type atoms, or the n-type and p-type extrinsic semiconductors, individually they are always neutral entities, neutral piece of semiconductors in totality. Okay, we can utilize this concept here. So also, what is the scenario in this piece? Now in this piece of extrinsic semiconductor, earlier when it was intrinsic, what was the scenario? There were neutral atoms which I am not showing, but there were some electrons and some holes, and the amount was same, so in totality it was neutral. And I am saying here what happens. Let's concentrate, because intrinsic case we already confirmed that it was neutral. So let's only concentrate onto the external or the inserted impurity. So if it is Nd, so all the Nd atoms are donating their electrons, so there are Nd number of negative ions. Positive ions, because one atom of pentavalent impurity will donate one electron, so the remaining thing out of one electron will remain a charged ion, positively charged ion, positive ion, which the concentration is Nd. Okay, and each this has provided one electron, and that electron only is the final concentration of electron we are assuming as N naught, because we always assume that finally the N naught is only significant, so this is N naught. Similarly, the holes are P naught, final hole concentration, and we also have, so if the holes have got detached from their parent external atom, so they leave behind the negative ion, which is, because almost all acceptor impurity atom are donating one hole. So when they donate one hole, the remaining atom becomes an ion, a negatively charged ion. So therefore we know that in totality this has to be neutral. This is what we have argued. The whole piece is neutral, the whole piece of semiconductor, extrinsic semiconductor. And if that has to happen, then the total positive charge must be same as total negative charge. So let us see total positive and negative charges. Total positive charge is number of positive ion per centimeter cube and number of holes per centimeter cube. So there are these two candidates, they possess the positive charges of single unit. So Nd plus P naught, and that must be same as total negative charge. So that negative charge is contributed by the electrons as well as the negative ion which are due to the donation of holes. So therefore it is N naught or Na plus N naught. So please watch it very carefully and understand this concept very carefully, because it looks confusing that Nd plus P naught. This Nd in a sense is positive ion, because Nd are number of atoms of pentavalent impurity who have donated their electrons. So whatever left behind, that is Nd, is positive ion. So positive plus positive charge should be same as total negative charge. So that's what it is. So this equation or this condition is known as charge neutrality. So please remember that intrinsic semiconductor was definitely a neutral entity as a whole. Similarly, if it becomes p-type or n-type, or even if it is a case of composite doping, the resultant has to have a neutral entity as a whole. Okay, then this thing, in addition to the mass law action. So these two cases, let me again finalize it. Now we are into the case of composite doping. Where we have donated Ni, means the scenario is earlier N was Ni, P was Ni, and we have added Nd also, we have added Na also. So when we add or we insert both types of impurity, then the whatever resultant becomes, that the whole process is known as composite doping. So the resultant is, let's say, N0 and P0. So we are finally interested in the resultant electron concentration and resultant hole concentration. That's what we want to calculate, and we'll be utilizing these two concepts: the charge neutrality, which is Na plus N0 is same as Nd plus P0. So this is one equation which we shall utilize, and another is N0 into P0. Once the final extrinsic has been formed, still it has to obey the mass action law, because if thermal equilibrium is maintained, we are not mentioning that thermal inequilibrium is there. So by default we'll assume the thermal equilibrium which we are trying to maintain. So these two equations, now you see you have two unknowns, Nd and Na will be provided to you, two unknowns and two equations. So anytime you can solve it, it's very simple, and it should be a problem dependent case. We should not formalize everything here, but just for practice, for some understanding, we are now going to see the cases, what may happen. Otherwise it is only now problem dependent. So whenever Nd and Na are given to you, we know this equation, we know the intrinsic concentration, or it will also be provided to you. So there will be two unknowns, N0 and P0. So we'll calculate N0 and P0. So the target parameters are this. So they are the target parameters. So we'll calculate two unknowns from two equations. Then we'll see if N0 is greater than P0. If N0 is greater than P0, it is N-type. So it is N-type if N0 is greater than P0. It is P-type if P0 is greater than N0. So that very quickly we can decide. Because if the final or the majority carrier concentration is of holes, or holes are the majority carrier concentrations, then definitely it is called P-type. If electrons are the majority carriers, then it will be called as N-type. So it's very simple to understand. Okay, but how to proceed? Just for the sake of some information, for some intuitive analysis, we will proceed with this. So let it be like I already declared that what is going to happen if it becomes, if the case is N0 is greater than P0. So finally it becomes N-type. Or if it becomes P0 happens to be greater than N0, then it becomes P-type. Although in the starting we do not know this, that which concentration is going to happen, because that's what we are trying to find. So we can proceed in any of the ways. So both the processes are equally similar. So if you see, if I take this equation, let's say equation number 1, and I keep the value from this, so Na plus N0 is equals to Nd plus P0 is Ni square by N0. Ni square by N0. So from 2 we have kept in 1, because here we are assuming that it is going to be N-type. We are assuming, we do not know the final one, but we are assuming that N0 is going to be greater than P0. So we should first try to find the majority carrier concentration. So therefore I am trying to solve into N0. So if N0, okay, so this is a quadratic equation and we know the roots of it using Sridharacharya formula, and that is N naught is equals to minus B by 2A, so by 2 that means ND minus NA by 2 plus, okay, all because it is very analytical to have a good numbers, this plus something, because this is a difference only, so therefore we should only expect the positive sign here. The same thing happens here. If we proceed in the same way, we are trying to find P naught here. If we are expecting that final semiconductor would be of P type, then we are expecting P naught to be there, so ND plus P naught is equals to NA plus N naught. N naught is Ni square by P naught. In the same fashion we can find the solution for P naught, because see, in N naught and P naught the equations are quadratic. So therefore P naught will also be same, but here it will be like Na minus Nd by 2 and plus under root of Na minus Nd by 2 square plus Ni square. So you see how to postulate about this is very simple. If general sense is if Na is greater than Nd, because these things will be provided to us, then we can proceed in this way. We can expect it to happen. There is no harm into this. Similarly, if the notion is that if Nd is greater than Na, then there is a notion that final concentration of electron should be greater than this, so we can proceed in this way. Okay, then if assumingly this is going to be the majority carrier concentration, hopefully, but if it doesn't happen, then also the equations and the processes are very well suitable and applicable. So if once N naught is known, then the other thing is very easy to understand. So that is Ni square by N naught. Similarly, if P naught is calculated here, then N naught is Ni square by P naught. So these are the exact calculations of carrier concentrations, independent of the cases whether doping concentration is more than Ni by 1 order or 2 order or 3 order or 4th order. It doesn't happen. It doesn't make any condition here. So these are the accurate calculations. Okay, and then very quickly we can see the cases out of it. You see the case, this thing is simple to calculate, so I'm just taking it out. And let's say case A, suppose, is perfect composite doping. If it is perfect composite doping, that means if Na is equals to Nd. How it could happen? Means you perfectly multiply, because these figures are into 10 to the power 14 or 10 to the power 15. We cannot be so precise. So even if there is a very, very small difference, we can approximately say that if N is equals to Nd. So this is a very, very rare case to happen. But if it happens, then we can say this becomes 0, this becomes 0, this becomes 0. So the result is N naught is equals to P naught is equals to Ni. This is 0, this is 0, so N naught will be Ni, then second one will also be Ni, or from here if you try to find, P naught is Ni and N naught will also be Ni. So therefore you find from anywhere. This is both the processes are correct. So therefore it results into this. So there is that's why this is not a favorable case, because we did the whole effort to come up with an extrinsic semiconductor, but finally what happens is the concentration of both remain same. So the final semiconductor will still be intrinsic. So the final semiconductor is still intrinsic. So this is just to understand analytically. This is a case which we cannot achieve, or you can say which we are never interested in. So we'll never use this case. So the next case also we can understand as a special case of this. A special case, let me call this case B. We are not doping anything, Na and Nd both are 0. Then also both are same, and then also you will be getting N is equals to P, N naught is equals to P naught is equals to Ni. So that is still the case of intrinsic. We know that if we are not doping anything, then that case is called intrinsic. So it is confirming our intrinsic case, N naught and P naught both are same and they are equal to Ni. That also you can keep anywhere. So these two are the cases which are not useful, and these equations are not mentioning any benefit out of this. So the main benefits of these two processes or these processes is to calculate the more relevant cases. Like if it happens to be N-type, if let's say Nd is greater than Na, or if Na is greater than Nd. Like these two cases only I am elaborating here. And in that also let us assume that Nd is greater than Na. So how this case can happen? That you have inserted some trivalent impurity, but the pentavalent impurity concentration is much higher than that. So that happens, or it says that Na is approximately 0. So that means or Nd is approximately 0. So you say that the donor impurity concentration is much higher than this, and that can only happen if you have not done any acceptor impurity concentration. So this indicates the case of N-type, making N-type semiconductor only. So therefore this we already can comment that the final one is going to be N-type. So finally it is going to be N-type. Similarly finally it is going to be P-type. So let us confirm our analogy here. So if it is the case, then we are mainly interested in majority carrier concentration first. So we'll try to use this first. So, and also then it is not relevant here because then it is Na minus Nd, and Na is less than Nd, so it will make it negative, and so therefore it is illogical to proceed in this way, and anything negative is not relevant, not possible. So we'll be trying to use this. So N naught is equals to Nd minus Na, because Na is much smaller than Nd, so this is approximately Nd by 2 from the first step. The second step here is Nd and Na is again neglected, so that is plus under root Nd by 2 ka square plus Ni square. We retain up to this only, and then we wait to see if there is an additional information. Then Nd was also much greater than Ni. If Nd is much greater than Ni, so you be up to this only. But if additionally it is provided that Nd is much greater, now what is much greater? We have already seen if it is at least 1 order or 2 order greater than that. So if it is at least a 2 order greater than Ni, like Ni is 10 to the power 10 for silicon, and you have at least 10 to the power 12 per centimeter cube impurity, or 10 to the power 13 or 10 to the power 14 or anything above it. So if that happens, then this Ni can also be neglected with Nd, because Nd square will be much greater than Ni square, or Nd by 2 ka square will also be greater than Ni square. So this will be neglected, and out of that we will be getting Nd by 2. Nd by 2 plus Nd by 2 will make N approximately Nd, and this is the majority carrier, and P therefore will be approximately Ni square by N, and N has been calculated as Nd. So we result, or we finally come to the same statement which we, before this topic we argued, that whenever there is impurity insertion or there is doping of one type of carriers only with respect to other, then this is the result. And we also know that we are making some doping concentration which is far greater than Ni. But if it is comparable to Ni, then restrict yourself up to this only. But when you are confirmed that the impurity concentration Nd is also much greater than the intrinsic Ni, then Ni could also be neglected here, and then so from this we can see that Nd could be neglected here, in front of Na. Here also Nd could be neglected. So we are only comparing Na and Nd up to this. We are not comparing Na and Nd with Ni until unless it is additionally provided. But by default we know it is a general practice that Na or Nd, whatever it is much greater than Ni. So that we can do, but let's do it stepwise. So if Na is much greater than Nd, then this is neglected, and P naught approximately becomes Na by 2, plus here also it is Na by 2 square plus Ni square. So I have cautioned you, if it is given that the doping concentration is comparable to intrinsic concentration or only 1 or 2 order higher, even for 2 order also this becomes much greater than this. So if the impurity concentration is only 1 order larger than the intrinsic carrier concentration, then you can carry out this thing only. You need not to make further assumption. But whenever the extrinsic doping or the impurity concentration is at least greater than Ni, at least with at least 1 order more, then you can say that further information is this, which is the general case most of the time. Then finally P will be approximately Na, because then Ni will be neglected. So only Na by 2 ka square will remain inside, and this will give you Na by 2 outside. Na by 2 plus Na by 2 will be Na. And similarly the minority carrier, which is electron, is Ni square by P. P is Na. So it is like this. So we have come to the same case. So please remember, these are the only, this set is the only relevant case in 99.9% cases, because the technology part of silicon, the processing part, or doping and implantation, oxidation, these things are highly rigorous. We do not start these processes blindly. We already have some simulation results or some practical figures into our mind, and then only people are, or industries, carrying some experiments. So it is not like once we do everything and at the end we come to know that okay, the final electron or hole concentration is so bad so that it is comparable to Ni. It doesn't happen. Whenever we are trying to make an extrinsic semiconductor, we are firmly, or we are well determined that we will make it a good extrinsic semiconductor. So it is very optimistic case that every time Nd will be greater than Ni if we are going to make N-type, or Na will be greater than Ni if we are going to make a P-type. So that will only be the case most of the time. But for the sake of some numerical practice, some problem statements, if the external doping concentration or the impurity concentration is not much higher than Ni, so that is only within 1 order or within 2 order, then we can keep formally up to this. We need not to further simplify. Or if Na and Nd both composite doping have occurred, and Nd and Na both are comparable, you cannot neglect one out of other, then we should further go up and we should try to utilize these two results. So this, then this, then this. So like this is the level of approximation. So everything is the part of numerical consideration, but once we have seen this, we are well confirmed that if it is not given, which is the case of most of the numerical, then we can blindly go for this case. Okay. So okay, now a small comment on the carrier concentration and nature of semiconductor, extrinsic semiconductor, as a function of temperature. So final Fermi level of extrinsic semiconductor is the indication of final carrier concentration, because with that only we can identify how much impurity doping we have done. If it is the Fermi level shifts much higher than the EFI, the center value, then we can expect then that the final carrier concentration of majority carrier is much higher. So as a function of temperature. So let us see this. What happens with intrinsic? Let us plot some figure here. Let's say, yep, then let's say this is 700. So this is scale of temperature, and what happens with intrinsic is at 0 degree Kelvin we know that everything is absolute rest, there is no thermal agitation, and there is no intrinsic carrier concentration as well. But as we increase the temperature, what we expect that at Ni this we have a very poor figure of, let's say, 10 to the power 10 for silicon. Then let's say here we have 10 to the power 12, and here we have some 10 to the power 14, some 10 to the power 15, 10 to the power 16, and like that. So this may not be a linear scale because the orders are increasing, so should be some logarithmic scale or something, but this is just to understand. Okay, so with this we know that we are somewhere here, and with intrinsic we calculated one numerical. In numerical we saw that when we go around 500 or 600 degree Kelvin, somewhere here, we found that for silicon, even if it is intrinsic, then carrier concentration, both electron and hole, both increase with the same amount, and they go up to 10 to the power 15. So that means it should be somewhere here. It is like this. So this is the graph for intrinsic semiconductor, or for Ni. N is equals to P. So at any point of this, at any point on this, we have N is equals to P is equals to Ni. At any point of this, we have, like at 300, just to quote some values, at this we had N is equals to P is equals to Ni 10 to the power 10 per centimeter cube for silicon. Similarly, at, let's say, 600, at 600 the value was 10 to the power 15 approximately, we calculated. But still, at any point on this curve, the number of electrons and number of holes will remain same, because this is the curve for intrinsic semiconductor. So at very low temperature, the number of carrier concentration, or the carrier concentration, is very poor, or there are no free carriers. But as soon as we increase the temperature well above the room temperature, then suddenly they try to increase with rapid rate, because 600, 700, it's too high. So this is a trend. But if on to top of that, if we try to show the extrinsic, then let us draw the Fermi level also. So this is the band gap, and this is conduction band edge. This is EC, this is EV. So you can see that the band gap is also a weak function of temperature. So if we are varying from here to, let's say, some same value, some 600 or 700 degree, we call it 800 degree Kelvin, then we know that band gap also reduces slightly. So it's a weak function of temperature only. So here it is, let's say 1.2 electron volts, or we call it Eg naught here. 1.21 electron volts for silicon I'm taking, and you know at 300 somewhere here around 1.1 electron volts. So there is a slight decrease in band gap. So the band gap is decreasing as we are increasing the temperature, but slightly. So we can forget this effect. We can say that okay, it's almost constant. Okay. So the interesting thing is to see the Fermi level always remains in between EFI. So even if the carrier concentration is increasing, but all due to the fact that N is equals to P, all due to the fact that N is equals to P, anywhere on this curve, N is equals to P is equals to Ni, all due to this fact that N is equals to P, the probability of that energy level where the occupancy is just half, that energy level always is at mid band. That is always at EFI. We know that is EC plus EV by 2. That is always in the mid band gap of the, because as soon as an electron is generating due to increase of temperature, the hole is also generating. So the probability remains exactly, the Fermi level remains exactly at this. But we know when the concentration of only one type of carrier increases, then some different phenomena will happen. So then what happens if you have an extrinsic semiconductor, then at near absolute zero, because there is no thermal energy, so everything would like to be here. The concentration is very, very poor, even if it is extrinsic. So we all start from here. But as soon as we go slightly above the absolute zero, as soon as it becomes 50 degree Kelvin, 100 degree Kelvin, or 150 degree Kelvin, in fact, it is still well below than room temperature. Then even at this low temperature also, it rapidly increases. Extrinsic semiconductor. So this is like this. So you can see that until and unless we come roughly close to this area, somewhere here, so this is the area, this is the case of partial ionization. That means you have doped for this complete chart, we have doped with a particular concentration. So on this graph, anywhere n is not equals to p, so you can assume any one of the case. So when n is not equals to p, then at any value you can see the majority carrier concentration. This is generally majority carrier concentration profile. So then any point of this, the majority carrier concentration is very high, and it increases significantly once we are out of 50 degree, 100 degree Kelvin. We are well beyond that, because if I said that when temperature is very, very low and it is near to absolute zero, then there is a fair probability of freeze out, or there is a fair probability that some atoms, impurity atoms, have not got ionized. So all due to that, the extrinsic carrier concentration will be well below. But the more important case is found to be here. In this domain, you see what is happening. You see both this red profile is for extrinsic semiconductor. So extrinsic semiconductor profile is going and it is merging with the intrinsic semiconductor. You see why this happens. At this temperature, there is n, let's say this is for pentavalent impurity, that is for n type. So n is approximately 10 to the power 14, let me say, or little bit more than that. And at the same temperature here, the Ni is approximately 10 to the power 3. So definitely at this temperature, the extrinsic semiconductor is definitely extrinsic. Okay, when we come here, well above the room temperature, around 400 or 450 degree Kelvin, then the N approximately goes to N naught, approximately goes to 10 to the power little bit, only 15, and at the same value here it shoots up, but still it is Ni is still around 10 to the power 11. Okay, but as soon as we come around 600, so you see at this, the N naught is approximately 10 to the power 15 only, little bit more than that, and Ni is also 10 to the power 15. That means as temperature increases, the internal covalent bond breaking increases. So there are lots of transition from valence band to conduction band for electrons. Similarly, when an electron is generated, one hole is also generated. So an original extrinsic semiconductor tend to become an intrinsic because the intrinsic carrier concentration has shoot up too much, so that it overshadows the extrinsic value. So it is like, let me give you like this figure. So we all started with at room temperature there was Ni approximately 10 to the power 10, and N naught was approximately 10 to the power 14, let's say. So this was happening at room temperature, 300 degree Kelvin. But when we increase the temperature, when it goes around 600 degree Kelvin, then what happens? Ni goes to approximately 10 to the power 15 for both N and P, and N naught still remains 10 to the power 15 or little bit increases, so because that is almost constant, so that also remains this. So therefore the minority carrier has also gone up, because Ni means both N and P increase. When we were here, then Ni means both N and P intrinsic were there. On to top of that there were electrons in excess. So the holes were very low. So P naught for maintaining the N naught into P naught is equals to Ni square should be like this. But all because at 600 degree Kelvin, you see, again I'll write it up. This has gone to, that means Ni, which is 10 to the power 15. So therefore, if I say that there is N naught, which was 10 to the power 14, then P naught is almost negligible. The P naught is almost 10 to the power 15. So it becomes comparable, or in some sense it is accessed. So that is not going to happen. Definitely it is also somewhere around 10 to the power 14. So therefore, if intrinsic carrier concentration increases, it overshadows the effect of external doping or external carrier contribution. But that only happens to a very high temperature, means well above 500 or 600 degree Kelvin. Well above 600 or 700 degree Kelvin, so around 700 or 600, then an extrinsic semiconductor cannot be identified very effectively. So the same thing can be shown here. So let's say this was the level of at around room temperature. This was the Fermi level, final Fermi level. But as temperature increases, we know that extrinsic semiconductor, we have got this understanding that extrinsic semiconductor try to become intrinsic. So therefore the Fermi level will try to come down like this or like this. Similarly, if we start with much higher concentration, then that will take some more time. So maybe this is for 10 to the power 14 and this is for 10 to the power 16 doping concentrations. So this is for ND. And what are these curves? These are the curves of Fermi level, EF. So I am saying that this is the Fermi level, this much below than EC. But as we are increasing the temperature and we are entering into this range, then intrinsic carrier concentration are shooting up. Therefore, an extrinsic semiconductor is indistinguishable from the intrinsic, because the minority carriers are also, they have the number is increased too much. So therefore, in order to indicate that extrinsic has become intrinsic, so the Fermi level should again come back to the intrinsic Fermi level. So therefore it is coming and it is lining up with this. Similarly, if it was P-type, so for higher concentration it goes like this, for lower concentration it goes like this. So maybe this was for Na around 10 to the power 16 and this was for Na around 10 to the power 40. So this is the Fermi level profile or Fermi level variation with respect to temperature. So if temperature increases, then the let me quantify it. As temperature increases, delta EF, which is EFI minus EF in the case of P-type and EF minus EFI in the case of N-type. So when delta EF reduces, that means for P-type EF will go up. For P-type EF is going up as temperature is increasing, and for N-type EF is coming down. So this is the summary of this picture, which is in coordination with this, the carrier concentration profile, and this is the energy band diagram explanation of the same thing. So the statement is, at this range of temperature, as temperature increases well above the room temperature, that means greater than or equal to, greater than, let's say 500 degree Kelvin roughly, then even an extrinsic semiconductor approaches to intrinsic semiconductor, or it becomes approaches or becomes, I must say, all because the minority carrier concentration goes to comparable with the majority carrier concentration. So it becomes comparable with this. So on Ni profile, the both N and P are increasing too much. So here N is also increased, P also increased, N and P both are increased. If both are increased, then you cannot distinguish that this is either majority or minority, which one is majority, which one is minority. And this figure, due to the covalent bond breaking, overshadows the extrinsic doped carriers. So with that, we can very clearly understand this concept. Okay. So degenerated means we are trying something, but exceptionally it is happening something else. Means we can have both degenerated N-type and degenerated P-type. What does it mean? Suppose this is the energy band diagram picture. If doping is much high, in the case of heavy doping, so this is the results from heavy doping. In fact, very heavy doping. So if the doping goes, that means ND for N-type, if it is greater than 10 to the power 18 per centimeter cube for silicon, and for P-type, if Na is, let's say, greater than 10 to the power 18. So if that range of doping is being performed, then what will happen? Like with, let's say, ND is equals to 10 to the power 19 per centimeter cube concentration, then now what is the case, that one extrinsic or the impurity atom is bounded by lots of silicon atom in neighborhood. So earlier with nominal doping concentrations like 10 to the power 14 and 10 to the power 15, this extrinsic semiconductor, this extrinsic or the impurity atom was not finding any same impurity atom nearby. So earlier this was the scenario. So in this crowd, one impurity atom was out of 10 to the power 6 or 10 to the power 7. Earlier we have seen so it is well bounded by lots of. So the general figure is that this distance is high enough for medium doping. That means one atom out of 10 to the power 6, 7 or 8 atoms of silicon. But when we do 1 out of 10 to the power 3, that means 10 to the power 19 because the total atoms of silicon are 10 to the power 22. So out of that we are doping 10 to the power 19. That out of 10 to the power 3 silicon atoms we are doing 1, or let's say 1 out of 10 to the power 2 of silicon. Then this distance between impurity atoms, or I must say ions basically, because they have donated 1 electron, reduces significantly. Then what happens? So if the distance between them will reduce because they will be more in concentration now if we are going up to this. That means when we are going for ND around 10 to the power 18 or 10 to the power 19 or 10 to the power 20, like that in this range, then the impurity ions or atoms will be close to each other, or this will find a nearby, relatively nearby, it is still much far, but relatively nearby another impurity. So there will increase lot of interionic interactions will happen. So this will result into impurity scattering phenomena. Sometimes it results into impurity scattering, or the donor energy levels is split. So earlier we expected that with the moderate doping this should happen, that one donor level will be inserted like this, where an electron is temporarily sitting and then very soon it comes here. But now this donor energy level splits, or it makes a band. So when it makes a band or it splits, so some part of it goes inside. So it is like this. So this is the range of possible range of ED. So therefore it looks like the donor energy level is splitting, and therefore the effective or the final Fermi level enters into the conduction band. So far we have not seen this case. We have seen that in small and medium doping the Fermi level increases up, because if it is n-type the Fermi level moves up, but always it remains below EC. But this is for the first time in the case of degenerated n-type semiconductors, all because the impurity atoms or ions have got very close to each other. They start interacting because both are ions, so their interaction is very important. Atom to atom interaction is not that much important, but ion to ion interaction is very significant. All because of that lots of abnormality happens, and all due to that the energy level shift, it splits, and therefore the final Fermi level is somewhere here, EF. So we can say the Fermi level moves in conduction band. So due to that, lots of abnormal effects come into the picture. Now we are not going to study this. We just postulate that this type of degenerated external or extrinsic semiconductor will not behave as a nominal extrinsic semiconductor. This will not behave like a nominal n-type extrinsic semiconductor. It will have some different characteristics, specifically temperature coefficient of resistivity or temperature coefficient of conductivity, which we'll discuss later on. But something abnormal will happen here, and all due to this effect. The same thing happens here. So for again the same thing, the impurity acceptor ions are coming to very much close to each other. They start ionic interaction between them, and this is highly dangerous interaction. So all due to that, the EA energy level, acceptor energy level splits, and the final Fermi level moves within the valence band. So this was the edge of EV, this was the edge of EC. So far we have not seen this. We have only seen that if we make a p-type semiconductor, then then final Fermi level shifts down, but it always remains above EV. But this is for the first time. For degenerated p-type semiconductor, the Fermi level enters inside the valence band due to the same argument. So again, so the Fermi level moves into the valence band. So the extrinsic p-type then behaves abnormally. So what are those abnormal effects? We need not to go into detail except one, which is required for the scope of this course, that is temperature coefficient of conductivity, which we'll see later on. So but something different to happen we are expecting, all due to this. So this is one point which we should remember for degenerated semiconductor, and this happens for very, very high doping. For silicon we are putting the figures because there are 10 to the power 22 atoms per centimeter cube. So okay, having completed all the basic understanding of the carrier concentration into the intrinsic as well as into the extrinsic semiconductor, now we are ready to go for some problems, some numeric figures, so that we come up with some better numbers of carrier concentration, at least with respect to what we obtained in intrinsic semiconductor. So in extrinsic semiconductor we can see very easily using some problems that we can achieve far better number of carrier concentration, and when we use these carrier concentration in the current conduction phenomena, then definitely a good current, a healthy current at commercial application is achieved. Okay, so the problem statement is very clear. A sample of n-type semiconductor has electron density of this, that means electron density is same as electron concentration per unit volume, and that could be confirmed by looking at the units per centimeter cube. So definitely it is electrons per unit volume at room temperature. So in this statement no specific silicon or germanium has been mentioned, so we need not to have any idea of Ni or atomic density prior. We need not to take it because I have told you that every time any standard data will be provided very well in the numerical. So so it could be any n-type semiconductor because it is n-type. So what we are expecting is that the electron concentration, this is definitely should be the majority carrier concentration. If the intrinsic carrier concentration in the sample is this, then find the whole. So the second statement tells us the prior condition, that means earlier when it was intrinsic, then there were these many numbers. So therefore Ni is intrinsic carrier concentration, this, and the majority, because it is n-type, so majority carrier concentration, which is n, should be Nd, approximately 6.25 into 10 to the power 18 per centimeter cube. And then we have to calculate the Hole's concentration. So it's very easy. Basically the problem's intention is to check about our knowledge about the mass action law. So because if nothing is mentioned, we always assume the case of thermal equilibrium. So at thermal equilibrium we know that N into P is equals to Ni square. So N is the number of electron concentration that is directly given. We have to calculate the carrier concentration of minority carrier, that is holes. So for P, this is Ni square by N, and Ni square is 2.5 into 10 to the power 13 square upon N is 6.25 into 10 to the power 18 per centimeter cube. So if we do it, you see the numerator comes 6.25 into 10 to the power 26 upon 6.25 into 10 to the power 18 per centimeter cube, and this is basically 10 to the power 8 per centimeter cube. So this is very easy. Now let me again brief the story what has happened. So earlier we had N in the intrinsic, let me call it intrinsic semiconductor. The N naught was equals to Ni and was equals to 2.5 into 10 to the power 13, and P naught intrinsic, both were same because it was intrinsic earlier, it was also Ni, and that was also same as this, the figure. Then we added Nd, which should be ideally in this order. We know that some part of Nd goes here, but it is some part of Nd, but for recombinations with the minority carrier it is too much, so it will reduce this thing a lot. So the final concentration will be N will rise too much beyond N naught. So finally it has reached approximately to Nd. What is this, which is directly given to us, 6.25 into 10 to the power 18, and P basically comes much lower than its intrinsic value, so therefore it is given by this. So this story we have already seen, but just for a quick recall we have seen it again here. Okay, so the next problem is calculate the resistivity or conductivity of germanium at room temperature. So basically we will be calculating conductivity here, and the inverse of that we very well know, that is the resistivity. So I will be only calculating up to the conductivity of germanium at room temperature for following cases. Means it is not intrinsic, not extrinsic. There are various cases, so one by one all are different cases. So first of all we have to calculate in the intrinsic case, then we have to calculate when this happens, when this happens, and when this happens. So let's go one by one. The required data is already given. The intrinsic carrier concentration for germanium is this. The electron holes and electron mobilities are this, and the atomic density of germanium is this. Okay, so with this let's come for the solution of first thing. Calculate the conductivity of germanium for intrinsic condition. This we have already calculated actually, but quickly if we want to revisit the value, then it is in the intrinsic case let us identify the conductivity formula. Sigma is, we know that it is in general NQ mu, where N is the number of concentration, carrier concentration, Q is electronic charge, single electron charge, and mu is the mobility of carrier. But we know that in any semiconductor, be it intrinsic or extrinsic, in conductivity or in current conduction, there is a contribution of both types of carriers. So basically in a more generic form we should better write it NQ mu N plus PQ mu P. And all because the first case is of intrinsic case, we know that N and P both are separately equal to Ni. So N is Ni, P is also Ni. So if I take Ni and Q common, this we have already done. Ni Q mu N plus mu P. Now if I keep the value, so this will be Ni as this 2.5 into 10 to the power 13. This is this. Q is 1.6 into 10 to the power minus 19. Mu N plus mu P is 1800 plus 3800. So what should be the unit? That is mho per centimeter or Siemens per centimeter. So let us calculate this. This comes as 0.0224 mho per centimeter. So this data we are well familiar with. We calculated this in the case intrinsic case A.1, section A.1, or sorry, section A.2. Okay. So this conductivity is a poor value. We argued there that this is the poor value, relatively poor value, because for silicon that was much poor than this, but still this value is also not very good. Okay, then let us come to the second case. Second case says that when pentavalent impurity is 1 in 10 to the power 7. So we have to again calculate the conductivity, but for this case. So you are doing pentavalent impurity doping, that means donor impurity Nd, and that is 1 in 10 to the power 7, means out of 10 to the power 7 germanium atoms we are doping 1 of impurity atom. So that means out of 10 to the power 7, if it is 1, then out of these many number of atoms per unit volume for germanium, how many impurity atoms will be there? So this is another way to give the concentration, impurity concentration or doping concentration. So we very well know that how to calculate this. So this is basically, there is 1 out of 10 to the power 7. So how many out of this? So this is 4.4 into 10 to the power 22 total upon 10 to the power 7 per centimeter cube. So every time we can do this. So this becomes Nd is 4.4 into 10 to the power 15 per centimeter cube. So this is the impurity concentration for donor impurity concentration. So when we are doing second case, we are only doing second case, then first and third and fourth cases are not applicable. So in this case the germanium semiconductor becomes extrinsic or n-type semiconductor with this number of majority carriers, because we know that earlier we had Ni 10 to the power 13 only. So but impurity concentration, the additional electrons from external doping, they go 10 to the power 15. So 10 to the power 15 is definitely 2 order greater than this. So we should not be in a doubt that we can neglect Ni or not. Definitely we can neglect. If anybody is interested in the detailed calculation, in the accurate calculation, you can go for that under root formula. So let me elaborate that also. So the accurate calculation is, it becomes n type, so n should be Nd minus Na by 2 plus under root Nd minus Na by 2 square plus Na square. So actually we start from here. This is in general formula for calculation of electron concentration, but very soon we know that Na is 0 here, so we are only remained with Nd by 2, not square, I'm sorry, plus Nd by 2 square plus Ni square. Now it depends. If we exactly calculate exact calculation, so if we proceed, we do not take any assumption, then we'll keep Nd and we'll keep Ni. So the N will come Nd by 2. Nd is this we have argued, so 4.4 into 10 to the power 15 by 2 plus under root this much, that is 4.4 by 2 into 10 to the power 15 square plus Ni square, so 2.5 into 10 to the power 13 square. So this we will proceed with, and this will give me 2.2 into 10 to the power 15. Okay, so this is 2.2 square into 10 to the power 15. 2.2 square will give me, that will be 2.2 square and into 10 to the power 30. So this will be the first term once you open the square, plus 2.5 square is 6.25 into 10 to the power 26. So now you see, when we have to add these two numbers, then definitely while adding these two numbers, this is 4 order greater than this, because earlier this was 2 order greater than this. So by taking square, this becomes 4 order greater than this. So it is like adding 1 into 10,000. So if 1 plus 10,000 is definitely very very close to 10,000 only, therefore it is illogical to retain this, and it will demotivate our calculation for the exact values. So it will say we need not to consider this case. So this whole term will be approximately 0 or much less than this term. So in front of this goes to 0. It's not absolutely 0 but relatively 0. So therefore from the very start we can expect from here that if ND Ni, so if ND is greater than Ni by more than one order, then we could have said that then Ni square could be neglected. If Ni square could be neglected, then this is Nd by 2 plus square under root, so that comes Nd by 2 and this becomes Nd only. So then N is approximately Nd, and this approximately is also insignificant because it is almost close to Nd only. So therefore this is 4.4 into 10 to the power t. So okay, let me make some space. So there is no need for exact calculation. So whenever you have a doubt, you proceed, but ultimately you will find that the exact calculation was not required. So both result into the same thing, and approximately Nd, which is 4.4 into 10 to the power 15 per centimeter cube, and then P, once the majority carrier has been calculated, or even if the minority carrier is first calculated, then the other one is directly obtained from the mass action law. So that says that this is Ni square by N. This is exact calculation, but we know approximately we are saying N is Nd, so this is Ni square by Nd. Now if I keep value Ni square, so that becomes 6.25 into 10 to the power 26 upon, I have done the square, so please mind it. Nd is this, so this is 4.4 into 10 to the power 15 centimeter cube. So P comes as, or the holes concentration, they are the the minority carriers. So it will come of the order of 10 to the power 9, around 9. So exactly it is 6.25 divided by 4.4, so that gives me 1.42. Okay, so this is 1.42, approximately 1.42 into 10 to the power 5 and 4, 9. So when the the electron concentration has increased from 10 to the power 13 to 10 to the power 15, then at the same time the concentration of hole has been reduced from 10 to the power 13 to 10 to the power 9. Okay, so now we can calculate conductivity of extrinsic semiconductor. So we'll be again starting with this concept. So when we start with this time P and N concentrations are not same as Ni, so they are separate values, so we can only take Q common. So Q will be taken as common, so this becomes N mu N plus P mu P. So if I write this 1.6 into 10 to the power minus 19, N is this 4.4 into 10 to the power 15 into mu N is 3800 plus P is 1.42 into 10 to the power 9 into 1800. Now you see in this addition again, in this whole addition, again we can approximate it. So you see what is happening here, all because this term, okay, this term is almost comparable. The order is almost comparable. I am not saying the value. Value is almost doubled, more than double value, but this is of third order, this is of third order. This is of first order. But what about this? This is 10 to the power 9 and this is 10 to the power 6 order more than 10 to the power 9. So it is again illogical or insignificant to add this plus this, because this only becomes the dominant term. So even if you add it accurately, you do lots of efforts, but this thing will vanish after 4 or 5th decimal. It will only impact after 4 or 5th or 6th decimal point. So therefore this is again waste of time to carry it. So what happens? So what we are neglecting this. So let me conclude it. It says So it says that the total conductivity is NQ mu N plus PQ mu P. All because Q mu P and Q mu N both are of the same order. Q is common and mu and mu P are almost of the same order with some double, triple or 4 times of its value. But the major comparison is this plus this. So if the variation is of more than one order, then it is insignificant to carry the smaller term. So here the n is greater than, so in this n is greater than p. N is this and p is this. So 10 to the power 15 and 10 to the power 9. So if it is happening, then it is illogical to add these two terms. So this only becomes nq mu n. That is what. So therefore, what do we conclude? We conclude that in extrinsic semiconductors, because majority carrier concentration always will go by 3 or 4 or 5 or 6 orders more than the minority carrier concentration. In any case, not even germanium, for any practical cases, the majority carrier concentration will definitely go up by some 4 or 5 or 6 order more than the minority carrier concentration. So in order to calculate the conductivity or current density later on, it is always illogical or not worthy to carry both the terms. So even if we do so, we are just going for some unnecessary accuracy which only comes after 4 or 5 or 6 places of decimal. So we can, at the very first place, we can discard the smaller term. So here the smaller term is this, because this corresponds to the conductivity of minority carrier. So we can only retain this term for a fair enough level of accuracy. So therefore this is only sufficient enough. So therefore if we now proceed, so this is we had written that first term, so this is 4.4 into 10 to the power 15. I'll have to write it again because I deleted it. 1.6 into 10 to the power minus 19 into mu n is 3800. So that much mho per centimeter. Mho per centimeter or Siemens per centimeter, both you can write. So once you do so, the value comes as, so the conductivity when it has become n-type. So this is the second case, is when the final semiconductor becomes n-type. So let me indicate it like this. So then the value is coming as mho per centimeter or Siemens per centimeter. So that is the final answer. Now you see, earlier in the intrinsic case is what it was this, now it has got this. So how much improvement do we see? The improvement is of 1, 2. So it improves by 2 order. So why only improvement of 2 order is sufficient in germanium? Because already the intrinsic carrier concentration is far better than what we see in silicon. So here, even if we only improve the carrier concentration by 2 order or 3 order, that would be sufficient enough to obtain the commercial range of currents or current density. So there is a far better improvement in the conductivity. So now if we apply an electric field, the majority carriers, effectively or dominantly the majority carriers will give the current density. There will be some current density contributed by minority carrier, but that contribution would be much smaller than the contribution of majority carriers. So we can say that overall conductivity or overall current density is only or dominantly given by the majority carriers. Okay, then the same procedure could be proceeded for the third case. So quickly let us see that. Okay, so the third case is, it says when trivalent impurity. Trivalent impurity means we are somewhere to calculate this. So let me again elaborate this, how do we make it. So we are making impurity, one impurity out of 10 to the power 8 host atoms. Host atom is the original germanium atoms. So out of 10 to the power 8 germanium atoms, we are making one impurity. So out of 1 we will be making 1 upon 10 to the power 8. So out of how many germanium atoms are there per unit volume? So out of this 4.4 into 10 to the power 22, we will be making 4.4 into 10 to the power 22 upon 10 to the power 8. So that's what we did for this also. The same thing we are doing, just to explain in detail. So therefore Na is 4.4 into 10 to the power 22 upon 10 to the power 8. So here, because out of more number of germanium atoms we are doping 1. Earlier we had only within 10 to the power 7 we were having 1. So there the doping concentration was 1 order larger, higher. But here, out of more number of germanium atoms, we are only doping 1 impurity. So here it is bit lower, only 1 order lower. So here it comes as okay. So now Na is calculated and everything then will remain same. So this is what, because it is 10 to the power 14 this time. So again we have to calculate the conductivity. For that we need to know, we have to start from NQ mu N plus PQ mu P. We'll have to start with this. For that we require N and P. So P, majority carrier concentration, is given by, always start with the generic case, Na minus Nd by 2 plus Na minus Nd by 2 square plus 9 square, and that is under root. Okay, so when we start with this, and additionally we know that Nd is not there, Nd is not there, we are only doing the trivalent impurity. So this leaves us with P is equals to Na by 2 plus under root Na by 2 square plus Ni square. Now you see here, again the question will come whether Na is much greater than Ni or not. Here it is, Na is this and Ni is this. So it is only 1 order greater than this. So here, if the answers in the options are very much close to each other, then we should go for more accurate result, or we should not try to cancelize Ni at the first place. Let us carry, and wherever we require we can cancel it out. But there is a simple guess, we can guess it, that once Na is 1 order greater than Ni, then once after taking the square it will be 2 order greater than Ni square. So therefore we can expect that ultimately we are going to have some approximation. But if you want to carry it out, then let me carry it out as it is. So P is Na by 2, Na is this by 2, that means 2.2 into 10 to the power 14 plus under root 2.2 into 10 to the power, this square will give me 84 into 10 to the power. So the square of this, Na by 2 is 2.2 into 10 to the power 14. So 2.2 square is this, into 10 to the power 14 square is 10 to the power 28 plus Ni square. So if I do Ni square, that is 6.25 into 10 to the power 26. Now you see, as was expected, this is 28, this is 26, and both the coefficients are almost same. Almost, there is a little bit difference. But because there is a major difference in the order, then this, comparing this 4.84 with 6.25 is not sensible. Okay, then what again we can say? We can again say it is something like we are adding 1 into 100. We are adding 1 plus 100, so that is approximately 101. So it is again, we need not to carry. So even if you carry it, it doesn't matter. So let me carry it accurately and approximately in both the sense. So accurately, if I do it, then I am getting, if I do not assume anything, I am carrying this term. So when you add these two terms, this term with this term, then the addition comes as 4.9 into 10 to the power 28. You can confirm it using your calculators. That means this plus this comes as this. So the only effect has come to the first place after decimal or the second place after decimal. So again it is irrelevant to take under root of this or directly taking under root of this. Both things are approximately same. So that's what I said. Even if it is 1 order greater than the impurity concentration is 1 order greater than Ni, again we can approximate the case, but still if it's your wish. But if it is more than 1 order, then definitely you can go for approximation. So here we tried it and we confirmed that okay, there's no much effect. So we can again approximately say that this is this plus this only, which was Na by 2 plus Na by 2 square is much greater than this, so Ni square will be neglected. Then This is Na by 2 only, which is 4.4 per centimeter cube. So these are the number of holes. As soon as we get majority carrier concentration, we can very quickly calculate N. So that is Ni square by P. P is approximately Ni square by Na, you can say, and therefore it is Ni square is 6.25 into 10 to the power 26 upon Na. Na is 4.4 into 10 to the power 14 per centimeter cube. So this comes as 1.42 into 10 to the power 4 and 4. It is, I'm sorry, 6 and 6, 12. Okay. So it is this. Now you see this is the concentration of N, and when again we try to do this, then N and P, because Q mu N and Q mu P are almost of the same order. So whether we should actually add or we can approximate will only depend upon the relative values of N and P. The value of N is this, 10 to the power 12 order, and value of P is 10 to the power 14. So again it is like adding 1 with 100. So again the conductivity of this P type, because finally this will become P type because this is the majority carrier, is approximately PQ mu P. This time this term will be neglected as compared to this. So this will be only PQ mu P. Now PQ mu P is this 4.4 into 10 to the power 14. Q is 1.6 into 10 to the power minus 19. And mu P is 1800. So this will be mho per centimeter. And this is coming around. So this is 0.1267, and the earlier value of intrinsic conductivity was this. So once we had doping of 10 to the power 14. Now you see this was not very impressive doping because already there is a carrier concentration of 10 to the power 13. So we only had a doping which is 1 order greater than that. So even 1 order is a much bigger amount than this, but still to have to achieve the extent of doping, the benefits of doping, we should at least go for 2 or 3 orders more than what the actual or intrinsic concentration is. So therefore we expected that because the doping is not far enough, so therefore the conductivity has also got improved by 1 order. So it is this. Okay, then we can go for the last case with composite doping of this plus this. Now it is said that we are going for the composite doping, case 2 and 3, means we are doing both at a time. So here we calculated ND from case 2, sorry, this is the case 4. So ND from case number 2 was how much? We calculated it was 4.4 into 10 to the power 15 per centimeter cube. And Na was how much? It was 4.4 into 10 to the power 14. So this we did. Once we did this, and then we wish to calculate this. Now because ND is greater than Na by 1 order, it gives an idea to go for the calculation of N first with ND minus Na by 2 plus ND minus Na by 2 square plus Ni square under root. And when we keep all these values, this comes as this minus this. So if I do so, then this value of N is, so out of this minus this we can take 10 to the power 4.4 10 to the power 14 common. So what remains is 10 minus 1, that is 9 into 4.4 into 10 to the power 14. This is very simple because you see what I have done, ND minus Na. ND minus Na, if we do, we can take 4.4 into 10 to the power 14 common. So within bracket it remains 10 minus 1, so that is 9 only. So 9 into this. Okay, then the same thing comes here, 9 into 4.4 into 10 to the power 14 upon 2 square plus Ni square is already 6.25 into 10 to the power 26. That is under root. So if I calculate this exactly, then it comes as 4.06 into 10 to the power 15. Okay, see, interestingly what has happened. This is the accurate analysis where we have not made any assumption. Both ND and Na doping have been performed and we have calculated the final electron concentration using the exact result. So using the exact result, it comes around this. But if we make use of an assumption that ND is greater than Na, because ND is greater than Na only, but if we make use of the assumption that ND is greater than Na and neglect Na, then what will happen? Then N will be approximately ND from here. Because anyhow 10 to the power 15 and 10 to the power 14 are at least 1 or 2 order greater than this. So Ni square will definitely be neglected. So therefore if this, then this is 4.4 into 10 to the power 15 per centimeter. The same thing will result here. Now you see the difference. With the exact value this comes as this because order is same. And with the approximate this comes as this. So there is only a difference of 1 decimal point. Now it depends. If the problem statement or the options are very much close to each other and we are expected to get accurate result, then we should proceed with this, because even the first order after decimal is important. But if in the answers, if there is no difference, if there is a lot of difference in the orders itself, suppose, then we need not to bother about the coefficients value. But if in the options, if there are very much close orders or orders are same and there is only difference in the coefficients, then we are expected definitely to go for the detailed calculation with this. So this is the exact one, this is the approximated one. Now forward we can proceed by our way, like we have to calculate conductivity. So I'm only going by this way, taking approximate calculation. Approximate calculation, here we have assumed that ND is greater than Na. Not very good approximation here. So please, I want to avail you that this is not very good here, because ND is only 1 order greater than this. So it is still preferable that if you wish to go with the accurate result, you should. So, okay. So with this only, with the approximate only, I am going. So N is this, and therefore P will be. Now then we should not rely on P, because once the majority or any one of the carrier is calculated, then the second one is definitely calculated by mass action law. So that will be again approximate Ni square by N, and N is Nd. So that will give me Ni square as 6.25 into 10 to the power 26 divided by Nd is 4.4 into 10 to the power 15 per centimeter cube. So you see, this will result in a case of, so this will come around 1.42, we have already calculated, into 10 to the power, you see, 6 and 5 is 9. So this is P and this is N. Isn't it a similar case of this? So all because while we added these two cases and we still assumed that this is far better doping concentration than this, or this is far better doping concentration than this, because it is still 1 order greater, but we still assume, otherwise you could have gone for accurate calculation. So if this is greater than this, then ultimately the results will be same as the second case. So it is just the second case, so the answer will be the same as in the second case. So sigma will be approximately sigma n, so whatever we obtained in the second case. So it is like this. So in the fourth case specifically, I just want to mind one very important thing, that there is only one order difference here. So it is not highly recommended that to quickly assume this approximation. So there is a small difference, but that is significant enough if the options in our in the given problems are pretty close to each other. Okay, so the next problem is like this. In a p-type semiconductor, the Fermi level is 0.3 electron volts above valence band at room temperature, that is 300 Kelvin. Find the new position of Fermi level for 350 Kelvin or find it for 400 Kelvin. So there are two different cases. So we have to basically use the relation of Fermi level movement with the temperature, and this we have seen analytically as well as in maths also. So let's see that what we argued analytically. That let me draw a picture for this. We saw that all if I change temperature onto this side, then the band gap reduces, as well as the, if this is, let's say, EFI, this is EC, this is EV, then for P type we check that if this is the case, then Fermi level comes like this. So earlier at room temperature, this is the case. So this difference is given as 0.3 electron volts, because it is said that the Fermi level is 0.3 electron volts above the valence band. Again, I said that you should not mind the reduction of band gap, because that's a weak function. So please do not go by this impression. I have shown for better accuracy, otherwise you can assume it to be constant. So only just concentrate on the movement of Fermi level, EF. So this blue one is the EF. So as temperature is changing, the EF is increasing, and ultimately at a very big temperature, around 700 or 800, the extrinsic semiconductor almost becomes an intrinsic semiconductor, all because of the lots of intrinsic carrier concentration rise. So that we have seen analytically. Okay. Then we have to calculate the new position of Fermi level for 350K. So if it becomes 350K, let me indicate it here. Let's say this is 350K, and at this is the new position. So we are expecting that this will increase because it will go too close to the Fermi level. So the extent of being extrinsic will reduce. It will more or relatively become intrinsic, relatively. And similarly we have to calculate at 400 Kelvin. So here we still assume a further shift. So these two values we have to calculate. Okay. So for that, please do not mind the variation of this EV that we have assumed constant. So we know that the relation between EF, EV, so this is very well known to us. We know for P type, P concentration, P is equals to, which is also equals to the doping concentration Na is same as NV, effective density of a state in the valence band, to E minus EF minus EV by KT. Please mind it, earlier it was EFI minus EV in the case of intrinsic semiconductor, but once it becomes extrinsic, EFI everywhere in the formula will be replaced by EF, final EF. So EF minus EV, EF minus EV. So from here we can find this. So therefore every time whenever this is required and concentrations are given, or this thing is given, then we can do a quick math. Otherwise we need to remember lots of different formula which are ultimately derived from one or each other. So we can find it NV by Na. So this is e to the power minus EF minus EV by KT is equals to P by NV. Okay, if it is minus, if I make it plus, this will get reversed, this will become NV by P. Also if I take ln both sides, then it is EF minus EV will be ln of this into kT. So this is kT ln of V by P. So the same relation could be taken as this. So both things are same. So once this side is given and we need to calculate any shift in Fermi level, we can use this. And if Fermi level position or EV or EF is given and we have to calculate the concentration, then we can use this form. Both forms are equivalent. So here we can utilize this. So earlier means at 300 Kelvin it is given that EF, let me call it 300 minus EV remains same everywhere, is K into T is 300 into ln NV and P are not given. So let me call it equation number 1 or equation number A. Now for the case 1, oh my god, I took 1 only because it was this. Okay, in the case A, because the new temperature is 350, I have to calculate here. So therefore the only difference will be EF at 350 minus EV will be KT, that is 350 into ln NV by P, that will be equation 2. So if I do 1 divided by 2, so if I do 1 divided by 2, I obtain this divided by this, and this EF 300 minus EV upon EF 350 minus EV is equals to, so this side KK will get cancelled, this whole thing will get cancelled, so only 300 upon 350 will remain, and this earlier value is given to us, EF 300 minus EV. This is EF at 300 minus EV is 0.3 electron volts. Upon this we need to calculate. So this is delta EF at 350. So that is 300 by 350, or this gives me delta EF at 350 is equals to 350 upon 300 into 0.3. You see it is expected because from this formula this shift, this is nothing but delta EF. So delta EF is in direct proportion to temperature, and that's what we were expecting. As temperature increases, the shift in Fermi level linearly reduces, because here it increases, but otherwise the extent of being extrinsic reduces. The extrinsic semiconductor becomes relatively weak and it moves towards intrinsic characteristic. So therefore it is direct proportion with T. So that's what is expected, that this will give me a value of what? Oh, it is interesting. So this will make it 0.35 electron volt. So therefore delta EF 350 is EF 350 minus EV. So EF 350 will be 0.35 electron volts above EV. So this value will be obtained. So this is 0.35 electron volts. So as was expected that this will increase by this. So it was 0.3 electron volts. Now it goes here. Similarly, you see, because it is a direct relation. So in the case B, for 400 Kelvin, for 300 Kelvin, let me linearize this thing. It was 0.3 electron volts above EV. For 350 Kelvin, it was 0.35 electron volts above EV. And for 400 Kelvin, similarly it will be 0.4 electron volts, because the equation is linear with respect to T. So this shift is linear with respect to T. So therefore we can very well expect that this is 0.4 electron volts shift. So this is 0.4 electron volts above EV. So like that we can expect that at 800 or at 900 it will be much more. So but you see it will not go beyond 0.55 because ultimately at 0.55 this will saturate like this, because this band gap is 1.1. I guess this is for silicon. If it is not mentioned, we can take it for silicon. So for silicon, the only maximum shift what we can expect. So this is the maximum shift what we can expect, and this maximum delta EF which can happen is only less than or equal to 0.55. The band gap by 2. Band gap is around 1.1, so it is around 0.55 electron volts. So if we are calculating some data beyond this value, there means we have committed some mistake somewhere. Okay, see, this is another problem. Again, it is related to the energy band diagram. It says that in n-type semiconductor, the Fermi level lies 0.2 electron volt below conduction band. That's what we expect, that it is very much close to the conduction band for n-type semiconductor. Okay, find the new position of Fermi level if concentration of donor atoms is increased by a factor of 8. So let us graphically have this scenario. What does it say is so let's say this is EF1. This is Fermi level EF1, which corresponds to the case ND1. That means when we have done a doping of ND, because this is N-type. So N-type is a result of donor impurity concentration. That's what is confirmed with the second line, donor atoms. So with the ND1 number of concentration, let's say it corresponds to EF1, and definitely we know that for N-type material with the donor impurity concentration, the Fermi level goes up from EFI. So this is EFI, intrinsic, just for the reference case. Otherwise, here it is not required, you can delete this information. But just to indicate that earlier it was, when it was intrinsic, it was at EFI, then it moved up. And how much it moves up is decided by ND. Higher the ND, it goes further up. So with ND1, it is at EF1, and this difference is told to us, and that is a 0.2 electron volt below conduction band. So this is conduction band. So the last value of conduction band edge is EC. So below EC it is 0.2 electron volts. Okay, so this scenario is given so far. So if it is EF1, so there is a fixed value EC minus EF1. That is 0.2 electron volts. Okay, then it is said that if the concentration of donor atom is increased by a factor of 8, so if I have a second concentration which is nothing but equals to 8 times of ND1, so that later on we can keep. So let's say ND1 goes to ND2, then EF1 goes to EF2, let's say. So what we expect, because we are increasing the donor atom by a factor of 8, we are increasing, we should expect a further shift of Fermi level upwards. So what we are expecting here, that here we should get EC minus EF2 should be at least a lesser value relative to this 0.2, because now we have moved like this. So this is new. Let me mark it like EF2, which corresponds to ND2. So therefore now the difference becomes this, and this is what we have to calculate. Find the new position of Fermi level. So we have to calculate this or this. Okay, so for that again we need to have a relation where EC minus, this is EC, where EC minus EF is involved. So these are two different cases, please remember. So this is the case with doping concentration ND1, the red one is the case with the doping concentration ND2. So then again we should remember that we will always start with N for N-type semiconductor, which is approximately same as ND for all the nominal cases. is equals to NC, effective density of states in the conduction band. It's a constant, e to the power minus EC minus EF by KT. So earlier with the intrinsic we used to write EFI, but for extrinsic EFI becomes EF. So like this. Also we can write, if somehow in this problem or in the previous problem everything was given in relative sense with the EC or EV, so therefore we use these formulae. Otherwise, if something is being given in the relative sense with EFI, then we could have used Ni e to the power EF minus EFI by KT. So this also is equally valid, but we cannot utilize this because here the everything is given in the relative sense with the conduction band or valence band in the previous example. So this is not useful here, but both the formulae are same. So we'll go for the first equation itself, and we'll try to write equation number 3 as ND1 is equals to NCE to the power minus EC minus EF1 divided by KT upon ND2 is equals to NCE to the power minus EC minus EF2. So please see, we could have made use of this or this. So when we make use of this, we are indulged into more complicated ln function. So we are again correcting ourselves and we are still making use of this. So this gets cancelled. ND by N1, ND1 by ND2 is equals to e to the power. Now if it goes up, minus EC plus EC gets cancelled, and minus EF1, or even if we try to write, we should not make it cancel because what value we only know is EC minus EF1. So let me write it like this. Plus okay, so when it goes up it becomes e to the power this. So therefore we can take this KT common. So KT is common. So minus, and this is plus by KT. Okay, when we do so, ND1 upon ND2 is basically, ND2 is 1 by 8. ND2 is the 8 times because is increased by factor of 8. So if we do it ND2 by ND1, which is 8, we just reverse it, we'll reverse this thing also. So this will be e to the power EC minus EF1 minus EC minus EF2 upon KT. So that's what we will be obtaining. Now we have to simplify this. Okay, for this we come here and this makes it EC minus EF1. EC minus EF1 was 0.2. So e to the power 0.2 by KT is separated from e to the power minus something we need to calculate. Let me call it delta EF2 upon KT is equals to 8. So therefore e to the power minus delta EF2 by KT is equals to 8 divided by this, or when it goes up it becomes minus 0.2 by KT, and KT is given to us. KT is 0. Then we can take it, we can take ln both the sides. So here if we take ln and if we take it positive, this becomes, everything becomes minus 1. So with that this becomes 1 by 8 and this minus 1 actually makes it plus. Okay, then we take ln. Once we take ln, this is delta EF2 is equals to KT ln of this whole value. So ln of e to the power 0.2 upon 0.025 by 8. Now you can separate it or you can calculate the total value. So this is 0.025 into ln of into ln of e to the power this value, which will make it free from this. This will be 0.2 upon 0.025 minus ln of 8. Okay, so if once we calculate this value, this comes as 0.148 electron volts. So this is delta EF means EC minus EF2. This is what we had to calculate. So therefore this difference, which was unknown, is 0.148 electron volts. So as we expected earlier, it was 0.2. So then this blue EF Fermi level, earlier Fermi level, goes up to the red level, means a new Fermi level. So as we expected, that EC minus EF2 should be a lesser value than 0.2. So that's what we are getting. So as if we increase a further doping concentration, so you see it's very interesting, we have increased the doping concentration by a factor of 8 times doping concentration we are doing, which is a great improvement in the doping concentration, but all because that thing comes only under ln. So therefore the result into the shift of Fermi level is not too much, but all because it is a small value, small unit of electron volt. So even this change from 0.2 to 0.148, so the shift is 0.2 minus 0.148. So this much is the shift in Fermi level. Once the doping concentration is increased by 8 factor, then this is the difference in Fermi level. So that is 0.2 minus 0.148. So this is how, and we should mind one more thing, that any time the position of Fermi level is indicated by either the reference from EFI, that Fermi level is this much electron volt upper or higher than EFI, or the Fermi level is below EC this much, or Fermi level is above EV this much. So we have already argued that the absolute value of any energy level is not defined. We cannot numerically code any specific value for a Fermi level, because it's an absolute sense, it is not measured from any reference. So we can only talk about the relative sense, we can only talk about the difference between two energy levels.